I'm making this video as a bonus in order to further explain how to resolve the twin paradox, or how there is no actual twin paradox. And this is partially inspired by Dalilet's video, which is about the twin paradox in curved space-time. I do recommend you watch that video as well. But again, this video is meant to kind of show how to kind of resolve the twin paradox when there's a circular orbit. So we're going to set up this scenario. We have spaceship A, who's going to be stationary right at this point. Again, we have an orbit, and we can assume there's a major celestial body here, or we can just say that's a big gas giant. It doesn't really matter. The important thing is B is going to move in a circle in this orbit at half the speed of light around this point. And he'll obviously experience time dilation because he's the one that's in motion. And the radius of this circle will be 70,000 kilometers, and the circumference of it, once you calculate that, which is 2 pi r, is 440,000 kilometers. So now, how would length contraction work in this case? Well, what it would do is the length would only contract in the direction of B's motion. So at this point, at this snapshot, this will actually be an oval. Okay, so again, we know the true size of this orbit, which would be the orbit according to A, is 70,000 kilometers. But because B is moving at half the speed of light in the direction of motion, there's length contraction. So as you can see here, according to B, if we're on B's spaceship, this is actually an oval. And most importantly, B is always on the longer side of that oval. Again, not only would, when B is here, not only would the radius of this oval be narrow at this point, A, according to B, will also become narrow. Now, depending on where B is, B will always be on the edge of the oval. As you can see here, when B is at this point, the length contraction occurs at this direction. So there is length contraction along here, whereas here will actually be the normal 70,000 kilometer radius. So although the true size of the orbit is 440,000 kilometers, the B, when B is in motion and kind of looking at the orbit from outside of his window, will actually see the circumference as 410,000 kilometers. And again, and B will see an oval rather than a circle. But what gets kind of even more interesting is that suppose there is a odometer on B's spaceship, the true distance traveled by B will actually be only a circle. Again, not an oval, because B will always be traveling at the shorter side of that oval, so B's true path will actually be a circle, just like the normal size. But the radius of this circle will only be 60,000 kilometers, and B will only ever travel 310,000 kilometers per orbit. Now, this is interesting because keep in mind, B's actual distance traveled is not only less than what A thinks B has traveled, it's also less than his own interpretation of the distance. Remember, B, from his perspective, the orbit is actually an oval that's 410,000 kilometers in circumference. But his own traveling, as according to odometer, should he have one, he has only traveled 380,000 kilometers, and he's in a perfect circle. So he sees an oval, but he travels in a circle. Again, because of length contraction in the direction of his travel. Now, according to A, B has traveled 439,000 kilometers, but according to B, he has only traveled 380,000 kilometers from his own perspective. And since both can agree on B's speed, which is 0.5 c, you can see they must have different time. Because if they're going to agree on the speed, but they have different interpretations of distance, then the only other variable that would change would be time. B would experience time dilation as his clock would be moving slower than A's, and once B hits A again, he will be younger than A. Again, this is a factor of both time dilation and length contraction. Length contraction leads to time dilation. Time dilation leads to length contraction. The two go hand in hand. Now, one very obvious question would be, now suppose that B is orbiting a planet at a very low orbit, would B's travel circumference, could that be less than the actual circumference of the planet? And the answer is yes. So if you have a satellite that's orbiting the Earth really, really quickly, the satellite's own orbit will actually be smaller than the circumference of the Earth due to length contraction. Although it sees its circumference being smaller than the planet's true circumference, it never actually enters the body of the planet. But one thing to know is that the ship's own interpretation of the circumference in this case is 410,000 kilometers, yet it only travels 380,000 kilometers. So it actually travels less distance than its interpreted distance of the orbit. Again, this is because of length contraction that only goes into one direction, and because it's going in this circle, it creates this oval effect. Even though its own interpretation, it will be traveling only as a circle. And the ship will always see itself as being on the longer side of the oval. And it's because it only sees the direction of its motion that has length contraction.